This is the second video on rotation. It's about torque and inertia. Torque, we should remember from last year, is the turning effect of a force. And to calculate torque, we multiply the size of the force by the perpendicular distance to the point it's turning around, the centre of rotation. The unit for force is Newton meters. If we look at the torque on a wheel, such as a pulley, we end up with two forces acting on the wheel. The one force, which is through the axle holding the wheel up, and the other force that causes the rotation. The force at the centre has no turning effect, as it's through the centre of rotation, has a zero distance. So the only torque that is applied is still F times R. If we remember Newton's laws from last year for linear motion, we'll remember things like if object is at a state of rest or moving with a constant velocity, it will continue with that unless there's an external force acting upon it. The second law we summarise as F equals ma. And the third law is if the object exerts a force on a second object, the second object exerts an equal and opposite force on the first. And those were Newton's laws of motion for linear motion. We can look at this in terms of rotation as well. With rotation, they're exactly the same, except for we change velocity to angular velocity, acceleration to angular acceleration, and force to torque. So that is where we're sitting. And you can see I've underlined the changes. We end up with an equation for the second law as torque equals I alpha. Alpha is the angular acceleration, you remember, and I is a thing called rotational inertia. We will come to that later. Here's an example of Newton's laws. An unbalanced net torque acting on a wheel produces an angular acceleration in the same way as an unbalanced force produces an angular acceleration in linear motion. From experiments, it's found that the net torque is proportional to the angular acceleration, just like force is proportional to acceleration. But this time, the constant in the equation is called rotational inertia, I. Now we need to look at what rotational inertia is. Rotational inertia depends on the mass. It depends upon the mass. But if we change that mass, if the mass increases, the rotational inertia increases. So we know now it depends on the mass of the object. When I added the extra masses, stuck them on, the rotational inertia would increase. So we've now got the mass there, but there's another thing that affects the rotational inertia. It's not just the mass of the object, but how that mass is distributed. So if these masses I added on, I change their position, say I move them to the outer edge, the rotational inertia has increased because it has moved from the centre of rotation in the middle of the circle. So not only is the mass of the object important, the distribution of that mass from the centre of rotation is also important. The further the mass is from the axis of rotation, the larger the inertia. So now we've got the larger the mass, the greater the inertia, the further the mass is from the axis of rotation, the greater the inertia. And this is summarised on this page. Just take a moment to read it through. People doing ballet and ice skating often change their position of their arms and legs to change their inertia. You can see with this example, sometimes he pulls his arms into the centre of rotation, and sometimes he has his arms and legs further away. And in that way, he changes his inertia, which is useful for when dancing. And we'll explain that in a later video.